In this video, I would like to find the points on the cone z squared equals to x squared plus y squared that are closest to the point 4, 2, and 0. Let me show it to you how it looks like. Okay, as you see, this is the graph of the cone z squared equals to x squared plus y squared, and the little blue dot in here is the point 4, 2, and 0. And I'm looking for the closest point to the blue point, so probably one point in here and another point in here would give me the closest point, as you see this shape. Okay, so let's solve the question algebraically. Okay, I'm gonna start by writing the formula for it. The distance between a point x, y, z on the cone and the point 4, 2, 0 has this formula. Basically, the distance between any two points would be the square root of the differences between the first coordinates square plus the difference between the y coordinates square plus the difference between the third coordinates square. Okay, now the closest point means the smallest distance, right? Means the smallest distance. So based on that, what I need to do is to minimize the function d. And as you see here, if I minimize the function that is inside the square root, basically I minimize the whole d because the square root doesn't play that much role. So what I need to do is to minimize d squared. So based on that fact, let the function f, which is a function of 3 variables, be d squared, which is x minus 4 squared, y minus 2 squared, plus z squared. Now, as you see the z squared in here, this is the third variable. But if I want to simplify the function and I just have 2 variables, I can rewrite this using the equation of the cone. It's just because basically the point x, y, z is on the cone. So I'm going to simplify the function by setting f to be x minus 4 squared, y minus 2 squared. Now instead of z squared, I just wrote equation of the cone, which is x squared plus y squared. Now perfect. I have a function of 2 variables, x and y, and I need to find its minimum. What I need to do is to find the critical points, and to find the critical points, all I need to do is to set the partial derivative with respect to y equals to 0 and with respect to z equals to 0. The partial derivative with respect to x, I'm going to use the chain rule here. 2 comes down, x minus 4 to the power of 2 minus 1 times the derivative of inside with respect to x, which is 1. The derivative of this one is 0 because I'm taking derivative with respect to just x. So y would be like a constant. Plus derivative of x squared, which is 2x. Derivative of y squared is 0. So I'm going to set this one equals to 0. And if y, I'm going to do the same thing. This would be 0 with respect to y. This one would be y, 2 times y minus 2. Plus this one would be 0, and then 2y equals to 0. Now let me simplify the first one. 2x plus 2x is 4x, and then minus 8 equals to 0. In that case, x is equal to 2. On this part, 2y plus 2y, so 4y minus 4 is equal to 0. So y is equal to 1. So the only critical point that I got is the point 2 and 1. So this is the critical point. Now, absolute minimum of this function f exists is just because there is the minimum distance from the point on the cone to the given point 4, 2, and 0. Okay, so based on this fact, the critical point that I found is the closest point that I was looking for. So let me put this function, this point 2 and 1 into the cone to figure out the third coordinate of the point. If I do that, z squared equals to 2 squared plus 1 squared, which is 5. So z is plus minus root 5. So the point 2, 1, root 5, and the point 2, 1, negative root 5 are the closest point to the cone. So I'm done.